Alright guys, so today we're going to take notes on electrostatics, specifically on field lines, charges, and free body diagrams that are going to be associated with those charges as they interact with other particles. And so we're going to take some notes. You had an introduction to this stuff in the simulation assignment you were assigned yesterday, 1001, electrostatics sims. Today we are going to be working on 1002.1 at the end of the period, charges and fields problem set. But let's go ahead and get into the notes for today. You should hopefully have some notes written down from yesterday. If not, then you're starting fresh. But if you did copy down some stuff as you read through that reading at the end of the assignment, or if you wrote down observations that you had as you completed the simulations, then you may already have some notes and you can jot down today's notes underneath those, because it is going to be building on what you saw yesterday. So let's start with the definition. If you see the word electrostatics, maybe what comes to mind is static electricity, because that is pretty much what it is referring to. Electrostatics is the study of electric charges. We are going to be moving into our units for the rest of the year on electricity and magnetism, and so this is going to start us out in that direction. We won't be dealing yet with charges that are flowing like electricity. We're going to deal with static charges instead in this unit. But again, electrostatics is the study of electric charges. A charge, when we talk about charged particles, and we discuss their charge, it is the extent to which that object or that matter, whatever it is, has more or fewer electrons than protons. And so you're literally going to go back to things that you learned in chemistry and that you reviewed, again, yesterday in that simulation. But if an object gains or loses electrons, then that object will obtain a charge. And that charge will be determined based on how many more or fewer electrons that object or particle has than protons. When we do calculations later on in this unit, you will need to know that the variable, the symbol for charge, is the letter Q. And then the unit for charge is the coulomb. It's a capital C. You may recognize that name from chemistry. You should have learned about Coulomb's law in chemistry, but we're going to go over it again. At least I think it's still in the chemistry curriculum. I know it's in AP Chem, but I think it's still in first year chemistry, but you may or may not remember it. That's okay. We're going to go back over that, not today, but later on. Okay, so again, charge, the extent to which matter has more or fewer electrons than protons. So when we talk about charge, obviously we are going to have to go all the way back to the structure of the atom and the particles that make an atom have charge and therefore make a group of atoms or any material have charge, and that is protons, electrons, and neutrons, although the neutrons aren't really going to play a role here because they're neutral. But you do need to know that protons are positively charged and that electrons are negatively charged, and we are almost exclusively going to be talking about the electrons whenever we're talking about all of the units that we do. Because again, those charges that those objects obtain are because they gain or lose electrons. It doesn't really have to do with the other particles in the nucleus of the atom, but just to remind you of those charges. So again, if something is positively charged, it means that that object has fewer electrons than protons. So number of electrons is less than number of protons. It is going to obtain that charge by losing electrons. It will become positively charged. If an object is negatively charged, it's because it has a greater number of electrons than protons. And again, an object that is negatively charged will have gained electrons from some source. And if the object is electrically neutral, it means that you have equal numbers of electrons and protons so that all of those charges cancel out and you have a neutral material or particle. All of this should be a review, not just from yesterday, but from chemistry. Okay, so when we talk about the force, when you have charged particles can exert forces on one another, and we can have this electric or electrostatic force, and it is the attractive or repulsive interaction between any two charged objects. Okay, so you've probably heard phrases before like opposites attract, and that has to do with things like this. When you have oppositely charged particles, you'll have a force of attraction. If you have like charged particles, then you'll have a repulsive force between them. But regardless, you're going to have some amount of force that exists between objects if at least one of them has a charge. All right, so again, I just mentioned this, but oppositely charged objects are going to attract one another. Objects with like charges, like they're both positive or maybe they're both negative, those objects will repel each other. Two neutral objects are not going to do anything. Okay, however, one of the questions that a bunch of people missed yesterday on the simulation, and it was in the reading, if you read that page, is this last one, a charged object and a neutral object. And they actually will attract one another. Okay, so a charged object can attract either opposite charges or things that are neutrally charged. It can induce a charge in them. And again, that would be theoretically something, honestly, that is probably an AP Chem instead of first year Chem. But you could have like dipole-induced dipole. They talk about that in chemistry. I used to teach it in first year Chem, but I don't know that they do it anymore. But we'll look at this as well, because you actually saw this in the simulation yesterday. Whenever the balloon that you charged up stuck to the wall had a neutral charge, but it didn't change the fact that they were attracted to each other. It induced polarization in the wall in the simulation. All right, electric fields. We're going to describe the region around a charged particle or object. That's going to be our electric field, and within that electric field, a force is exerted on other charged particles or objects. So if you have a charged particle, then in the space around that particle, you have this field that would cause other particles to be either attracted or repelled, depending on their charge. You can't see the electric field, but we are going to represent it today with electric field lines, but to show the direction of those forces. Again, you need to remember when you think about electric fields, the same rules we just talked about: opposites attract and like charges repel. You should definitely write those two statements down if you haven't already done so, because you need to know that for not just this unit, but later on when we do magnetism, same thing. Opposites attract, like charges repel. All right, so again, we can draw field lines to represent the forces present in the region around the charged particle. These diagrams are used to show the type of charge. We can represent, the way that we draw it can show or designate whether or not that charge is positive or negative. It can show the relative strength of the charge. Is it a strong field or is it a weak field? Does that charge have, is it really negative or just a little bit negative? So you can show that with our electric field lines. And then you can also show interactions between multiple charged particles. So it doesn't just have to be one. You could have three of them in there, and you could have an electric field line diagram showing the field lines that exist in that space between those particles or around those particles, however many there are. So here's the rules for determining or how to draw your field lines based on charge. Okay, so again, you'll probably want to write this down, and you may even want to draw some pictures for this part. But field lines are drawn to represent the force acting on a positive test charge. That was just the definition they chose. It's somewhat arbitrary, but it is the definition we use. Okay, and so when you look at these field lines, they're going to have arrowheads on them, and those arrowheads are going to point in the direction that a positive charge would move. So if you look at the field lines around my negative point charge right here, they all point toward it, and that's because if I had a positive charge in that space, it would move toward the negative because opposites attract. Okay, and so for your negative charges, your field lines are drawn toward the negative point charge. You draw them with the arrows pointing inward, and that's because that is the direction that a positive test charge would be pulled. On the other hand, if you are trying to represent field lines around a positive charge, all of those are going to point away because, again, like charges repel, and these field lines represent the direction that a positive charge would move. So if you put another like proton in this space, it would move away from this positive charge, and therefore all of the arrowheads are pointing away from my point charge right here. And that's what it says. Field lines are drawn away from the positive point charge. So that's just the definition. So if you look at a field line diagram and I say, what's the charge of, point B, and point B has a bunch of arrows pointing away from it, then you can tell me it's positive. Okay, so that's kind of how you'll see that in question form later on. Okay, so the first thing we can tell about our charged particles is whether they're positive or negative, but we can also tell, the second thing we can tell is how strong that charge is. And we can tell by looking at the field strength density, okay, or the density of the field lines is going to tell us how strong the field is. So that's what it says here. The density of electric field lines shows the strength of the field at that position. More lines means a stronger field. So if you look here, all of these charges are positive. All of them have arrows pointing away. However, they have different numbers of them. And so even if they weren't labeled, and mine are, it says plus, +2, and +3. Okay, but even if they weren't labeled, I could tell that this one all the way to the right is definitely a stronger charge than the one on the left because we have more field lines. Okay, and so you can look at the density of the field, and that basically how closely packed those lines are together is going to tell you how strong your field is. So if you have a whole lot of lines in that space, then you have a really strong field at that point, which means you have a strong force that would be exerted onto any other object in that space. All right, so again, you can also show the interactions between charges. So we've got positive charges, we've got negative charges, we can show their strength, but you can also see this attraction between opposite charges or the repulsion of like charges with the field lines. And so that's what you see up here. Opposites attract, like charges repel, and that can be illustrated with the direction and bending of the field lines. So if you look at this image here on the left, you can see this is a positive and a negative charge, and the way that the field lines are drawn, it shows the same rules that we've looked at, but now being applied to those two charges. It shows that they're attracted to each other. You can see that all of the field lines point away from the positive charge, and all of the field lines point toward the negative charge, and you see this attractive force that exists between them. It would theoretically pull one toward the other. On the other hand, if you look at the image on the right-hand side, you can see repulsion. You have this big void in the middle because both of them don't want to be near each other, and so your field lines show that too. They curve up and away as they, instead of radiating outward like they were before, because again, these are repelling each other. This, by the way, is the same shape you're going to get if you have two negative charges next to each other. It will look the same shape. The difference will be the direction of the arrowheads. Okay, so if you have attraction, you're going to see this shape here. If you have repulsion, you're going to see this shape here of your field. Okay, so you should be able to answer questions about that later on as well, and I'm sure you have some in your assignment today. All right, so let's see if we can apply some of this. So I have two charged particles up here. They're labeled Q1 and Q2. So take a look at that diagram. Look at Q1 there at the bottom. Is Q1 positive or negative? Yeah, so you just have to look at the direction of those arrowheads, and I heard a few of you say it, but it is negatively charged because the arrowheads are pointing toward it. Okay, what about Q2? What's the charge of Q2? Yeah, it's positive. Okay, because the arrowheads are pointing away from it. Okay, and you can also tell that these are attracting each other. It has that same shape like we saw a second ago. Which one has a greater magnitude of charge, Q1 or Q2? Q2. See, I told y'all are going to think this unit's really easy because this is pretty much it. There's one calculation we do later on, and that's the whole thing. Okay, so Q2, and then how do we know? Again, there are a lot more field lines around Q2 than there are around Q1, so we have a denser field, and thus that indicates a stronger charge, a greater magnitude of charge. Questions about that? I got another one. All right, Q1 in this image, I know this is a little smaller. This is Q1 on the left, Q2 is on the right. Again, if you want to draw any of these pictures, you can. Okay, what are the charges of Q1 and Q2? Let's start with this. Do Q1 and Q2 have the same charge, or are they oppositely charged?
Same.
They have the same charge. I can tell based on the shape, okay, of those field lines. Okay, now are they both positive or are they both negative?
Positive.
Again, look at the arrowheads. Yes, they're both going to be positively charged because the arrowheads are all pointing away from them. Okay, which one has a greater magnitude of charge? Q1. Okay, because it has more field lines. Okay, let's try this. We haven't done this yet. Okay, let's draw a free body diagram for the electric force acting on Q1 and Q2. So, first of all, should these two charges attract or repel each other? I just heard it back there. They should repel. So when I draw this, I'm going to draw it so that my forces are repelling each other. Okay? Now, actually I had it up there, but which one should have a greater force? Between these two, if they're repelling each other, which one's force is going to be greater? They should be the same. I had it up on the screen a second ago. I took it back off. Okay, this is still force pairs. Okay, for every action there's an equal and opposite reaction. Still the same thing that we've been talking about. So you would draw them like this. It doesn't matter that this has a greater magnitude of charge than this. The force that exists between them will be equal and opposite. So they will have equal and opposite forces. Now, if we increase the amount of charge on either one of these, for both of them that force would increase the same amount. If we decrease the amount of charge, that we have here, then they would both decrease by the same amount, but they would still have equal and opposite charges regardless. Okay, so it doesn't matter that this one has a greater magnitude of charge. My forces of repulsion here are going to be equal and opposite. All right, so now I have two positive charges, and I have 3 points labeled in the field A, B, C. At which lettered point is the field weakest? How do I know how strong or weak the field is? What do you think, Alex? How do I know?
If it has less lines.
Yeah, fewer lines, sure. So if it has fewer lines, it'll be weaker. So where do you think it is weakest? C. Yeah, point C. Those lines are farther apart, so you'd have the weakest field at that point. Okay, if a negatively charged particle was placed at position A, what would occur? If we put a negative charge at point A, Mason, what do you think would happen to it?
It would attract.
Yeah, I would move toward that positive charge because opposites attract. Okay, now if we put a positively charged particle at point B, same idea, it would move away. That's the direction of the lines. Remember, those lines are pointing in the direction that a positive charge would move. So it would move along one of those field lines, okay, or kind of parallel to it at this point because there's not one drawn right there. All right. So let's try this then. I can't remember if you had pith balls in the simulations yesterday, but pith balls are basically balls that have a metallic coating on them. So they're usually made out of styrofoam or something really lightweight, and they have a metallic coating on them that you can charge. Okay, and because they're so lightweight, if you charge them up, you can see them actually move either toward each other or away from each other depending on their charge. So it says here, imagine two identical neutral pith balls, each hanging from strings as depicted to the left. Draw a free body diagram of each. So what forces do I need to draw for? Let's just look at one of them. What forces are acting on this pith ball?
Force tension.
Tension, yeah, there's a string there. Okay, tension should go up. What else?
Gravity.
If they're neutral, that's it. Okay, so if they're neutral, we're just going to have force of gravity down, force of tension up, and since it's just sitting there motionless, those forces should be equal to each other so that we have balanced forces. Okay, they would both look like that. Okay, now if we charge them, which is what we're going to do now imagine that the pith ball on the left is given a positive charge and the one on the right is made negative. Now we have to add that electric force, that force of attraction or repulsion. So first of all, should these attract or repel?
Attract.
They should attract because one is positive, one is negative. And so I need to draw that like this, okay, to show that they would be attracted toward each other. Again, those forces should be equal and opposite regardless of if the pith balls have the same amount of charge. Doesn't matter. Those forces are always a force pair. If this pulls on this, then this pulls back on that one. So make sure you draw them equal and opposite. All right, guys, so as I said, I think y'all are going to find this unit a little easier than the previous one. If you'll make your way to My Open Math, you have an assignment for today, 1002, Charges and Fields Problem Set, that's due by 11:59 p.m. tonight. If any of you did not submit your assignment yesterday, 1001, Electrostatic Sims, please turn that in for late credit. If you weren't here, you can come talk to me about that. It won't be late, obviously, if you were absent. But go ahead and get to work. You're welcome to help each other out, ask questions if you have them, refer to those notes that you just took. And again, make sure that you get it finished. We'll try to get it done in class, but if not, by 11:59 p.m. tonight.